Okay, so we are in Chapter 7 of the second edition of Statistical Rethinking. We're looking at questions 7E2 through 7E4. These are all very similar, so I thought we would just knock these out all in one pass. Okay, so I have all the questions listed up here. So basically what we're doing is we're looking at different situations and then calculating the entropy. So we're going to do that, and I'm going to calculate entropy in a few ways. Okay, so in the previous problem, we saw a few different formulas for entropy, and so I'm going to use a couple of those in each of these problems. I'm also going to simulate data according to the problem, and then calculate the entropy from that problem. Or from the generated data, which should more or less correspond to the theoretical calculations using probabilities that we assign rather than discover through the data. We'll also use a package called the entropy package to calculate just in another way. So we're just calculating this in a bunch of different ways. Okay. So before you do anything, make sure that you install and load this entropy package. Not that you need to. Unless you want to use the entropy command that is part of this package. Okay. So the first problem is, so we have a coin that is weighted, so it comes up heads 70% of the time. So what is the entropy for this? Okay. Well, we need to define the entropy. Oh, I'm sorry. I'm also going to calculate the maximum entropy for each scenario, just to compare all of this. Okay. But anyway, so we have a weighted coin that comes up heads 70% of the time, and then the rest of the time, 100% minus 70%, it comes up tails. Okay, and then of course the maximal entropy is just 50-50. Right. So here's one way that I'm going to calculate the entropy, and here's the other. Okay, so the first way corresponds to this command here, and the second way corresponds to that formula there, and the second way I'll calculate it corresponds to that top formula there. Okay, and then I'll also do the same for the maximal entropy. Again, the maximal entropy occurs when all of the outcomes are equally likely, and that's what I've done for max p. So that's what I have here, calculated in two different ways. Okay, so if I take these first top two lines, okay, this is the two ways that I calculated the entropy, and then and you'll notice that they're the same, obviously. Which they should be. And then here's the maximal entropy if heads and tails were equally probable. Okay, so there's that. Yeah. So now I'm going to simulate some data. I'm going to simulate 100 coin tosses of heads and tails. Okay, and I'm going to discover what the probability is from that simulated data. It should be about 50-50 because I'm using. Or I'm sorry, not 50-50, but 70-30, because I'm using this vector here, but it won't be exact. And so I'll calculate the probabilities. Okay, so I have that. Here's the probability of heads. It's how many heads come up in my 100 samples divided by 100, the length of my 100 samples. Okay, and then same for tails. Okay, and again, I'll calculate entropy in one of the ways that we saw. Okay, in this way. As well as with the entropy package using the entropy command. So I'm going to run this. And so we see that with our sample of 100, okay, we have our probabilities are actually kind of far from what the prescribed probabilities were, and this is just sampling bias, right? So here it's about 80 and 20, and you'll notice then that the entropy measures are different. Notice that they are less than our initial calculation with the prescribed probabilities, and this should make sense, right? So one of these outcomes is even more probable, right? Which means that we're less uncertain about the outcome. Okay. Now, if I had more data points, so now I have 10 times more data points. So this gets us much closer to 70-30, and then the corresponding entropy calculation is much closer to what we found initially. Okay, but I'm going to keep it at 100 just to show that sampling bias. Okay, well, yeah, okay. Okay, so for the next problem, we have a four-sided die, and it's loaded so that the one face shows up 20% of the time, the two face shows up 25% of the time, The 3 face shows up 25% of the time, and the 4 face shows up 30% of the time. Okay, so just going through the same process. So here's my probabilities, okay, that I just read out for 1, 2, 3, 4. Okay, the maximal entropy here would be as if they're all equally likely, equally probable. And now here's how I'm going to calculate entropy: one way, two ways. Okay, and then here's how I'm going to calculate the maximal entropy: one way, two ways. Okay, so when I run all of this, okay, so again, here's my entropy calculated in 2 different ways. They're the same. And then when all of the, and again, notice that this is less than the probability, or less than the informational entropy when all of the probabilities are equal. Okay, so yeah. So anyway, as we deviate away from everything being equally likely, the entropy goes down away from the maximal entropy that's achievable. Okay, and once again, I'm going to simulate some data. So I have my outcomes 1, 2, 3, 4. I'm going to sample those outcomes with the sample command. Okay, I'm sampling the outcomes with the sample command. I'm going to draw 100 samples. Okay, with replacement, which just means I can draw each one of these things more than once, which is necessary, according to the probabilities that I've described up here. Okay, and then I'm going to calculate the empirical probabilities. Okay, with the table command. Divided by the length. So the table will just give me a count of how many times 1 comes up, 2 comes up, 3 comes up, etc. So when I divide that by the total length, I'll get the probability of each of these things. And then again, I'll calculate the entropy by hand and with the entropy command from the entropy package. Okay, so I run all of that. Okay, so here's my implied probabilities from the randomly sampled data. Okay, and so the probabilities are not quite right. Okay, so so that should be 20, this should be 25, this should be 25, and this should be 30, but they're close. Okay, but nevertheless, so we get our estimated entropy, our empirical entropy, based on the data from these from our generated data set. Okay, notice that this entropy, okay, is much closer to the maximal entropy than the actual prescribed probability. So what does that tell us then about what happened in our data sample? Well, it means that all of these came closer to one another, or in general, all of the probabilities went closer to being evenly distributed compared to what they were in the prescribed probabilities. Okay. So the last one. So now we have a 4-sided die, but 4 never shows up, and the other 3 sides are equally likely. Okay, so I have 1/3, 1/3, 1/3. There should also be a 0 here that I'm just omitting because it causes some problems when we run the calculation, but that's no big deal. And now the maximal entropy here again is 25% for all of them, for all 4 faces. Okay, so I'm going to calculate the entropy in 2 different ways. And then I'm going to calculate the maximal entropy. Okay, so the maximal entropy should be the same as it was in the previous problem, and this is the found entropy. Okay, so again, so this is kind of interesting in a couple of different ways here. So so one reason that this is interesting is our prescribed probabilities are basically a uniform distribution spread among 3 options. The problem is we have 4 options, okay? But we're basically comparing the uniform probability distribution of 3 outcomes versus 4 outcomes, and just like we learned in the previous video, one of the things, or one of the desirable features of a measure of uncertainty is that as we have more options, entropy should increase. In fact, that's what we see here. Okay. So finally, I'm going to generate some empirical data with all of this. Okay, so I have 4 possible outcomes, but again, the 4 is not actually an outcome, so I'm just omitting it here. So again, I'm sampling my outcomes, 100 of them, with probability P described up here. Okay. So I run all of this. So the implied probabilities, okay, they're all close to a third, right? They're not quite approaching that, right? Or they're approaching a third or whatever, but they're not quite a third. And then here is the estimated entropy, or the empirical entropy that's been calculated. And again, So these are deviations away from a completely uniform distribution. And notice that this value right here is a little bit lower than this value, right? And this value up here would be the maximal entropy over 3 options, okay? And so here over 3 options, we are not quite uniform and we're just a little bit less. Okay, that is it for this.